thanks everybody. Thanks for the introduction. My name is Amogh. So I'll be talking about x86 instruction usage among C++ applications. This is joint work with some of my lab mates and two of my advisors. This was carried out when we were all at Stony Brook, but we've since dispersed to many other places. So briefly, we'll be talking about the relative importance of different aspects of the ISA, for example, instruction sizes, CPU extensions, feature sets, things like that. To give you a little teaser, here's the distribution of instruction sizes, this is binary encodings, in our data set. I'll get to how we gathered this and all in a second. x86 instructions can be 15 bytes in length at max. We find that the 14 and 15 byte instructions don't occur. And as we can see, things are skewed a little towards the smaller instructions, which means the ISA designers kind of did their jobs pretty well. They got the most used instructions of the lower encoding size, so binary size is overflay. So let's get into it. So first up, what is an instruction set and why are we talking about it? Well, an instruction set, as most of you know, I'm sure, is the interface that a processor exposes to software, right? So it consists of the supported operations, the set of instructions, any program visible state such as register, and its semantics like the memory model, consistency, etc. Examples of popular ISAs, x86, ARM, RISC-V's gaining a lot of momentum lately. So all this is fine. So most of you might be wondering, well, why do I care? Most of the time I write code in high-level languages, and compiler produces this code, code in binary form, right? Well, a lot of software tools do operate on the ISA. They take it as input, actually. So emulators, simulators, symbolic execution engines, and binary translators, although we're seeing less of these days. So, what is the actual problem when you're trying to implement one of these? What do you face? Well, a lot of the ISAs that are in use, that are popular today, are incredibly complex. For example, x86-64 has 981 mnemonics. Mnemonics are what we typically think of when we think of instructions. Something like add is a mnemonic. And those 981 mnemonics correspond to 3,700 binary encodings. That's what the machine understands. So if you have to support that much, that many binary encodings in a translator or an emulator, it's a lot of work. ARM similarly has a large number of mnemonics. So how do we prioritize, right? Like we want maximum returns on investment for developer effort. Well, all previous approaches have been kind of ad hoc. We've either looked at a benchmark suite and said, what does this benchmark suite use? And it will support that. Or maybe you have a target execution environment and then you collect a trace and you target that. But it only works in that form. It's kind of, then you end up in this realm where, this is coming from the VMware paper where they were saying, they used to get calls from customers saying our applications don't work, and then go check and be like, oh, we have to implement these things as well, and so that's on demand. So my assertion that I hope to convince you of by the end of the talk is that we can actually do better, because there's ways to figure out with good data what the relative importance of how importance is distributed across the data set. So, okay, how do we do this? Well, simple. We just go ask the users what they want. It would be nice if we could just do it, with that thread, but life's not that simple. So how do we do it? Well, sorry. The first thing we need to figure out is what instructions are in binaries. So, we go and calculate instruction footprints, that is all the instructions that a given binary uses. We do this by linear static analysis. We can get into why that particular choice of analysis method in later if we have time, or it's in the details are in the paper. We analyzed about 9,000 packages from the Ubuntu apt repositories. Packages is just the unit of distribution in apt. And once we had that, so we have a visualization tool that I'll show you at the end of the talk that you can explore the raw data in. And once we had the instruction footprints for each package, you have to figure out, like, are these packages uniformly important to all users? Well, to figure that out, we took advantage of data that's being collected by both Ubuntu and Debian. There's about 3 million installations that we draw from, and we use the so this data is what packages are installed in a given installation of Ubuntu and Debian, and based on that we calculate which packages are more important. So if a given package is installed in every machine, then it has very high importance, and on very few machines it has low importance. We use that to weight the instruction footprints that we calculated, and that's how we derive the data set. So now let's look at a use case of this data. Say you're developing a emulator, and you wanted to know what should I do first? Well, so we're gonna take a look at that in a second. First, let me define two metrics that we will need to figure that out. One is instruction importance. It is the probability of a particular instruction occurring at least once, at least in one package on a machine. And the other one is weighted completeness. That is, if you implement a tool that implements a section of the ISA, how many packages in the Ubuntu repositories, or how many packages that we considered in our data set can you support? So yeah, if you were implementing a emulator, for example, one way, the first thing most people would do is implement Hello World, right? That you want to support Hello World, and that actually takes about 30 instructions. So you get there, and then you're like, okay, where do I go after this? You could go to benchmarks. That's typically how we've done it. But we actually find that there's a much better approach. When you look at the instructions in order of importance, these are mnemonics, and if you do the implementation in the order of importance, you need to implement about 230 instructions, and you've actually covered 90% of packages that are installed on those 3 million machines. So what this tells us is that there's this long tail of instructions that only need to be supported if you're interested in supporting these small 10% of packages, and you can iteratively get there. Also, another thing to notice is that this graph is, while at points linear, there's actually places where there's elbows, right? And the paper has more details about this, but you can actually find applications that you can use to test each of these points. And so you can kind of have an iterative test-driven development cycle. Okay, so another question you may have is, should I support vector instructions, or should I support SIMD instructions? So to check this, we took all the different feature sets, the different CPU extensions that Intel has, and we calculated a baseline which is all scalar instructions. So there's no SIMD in here, and we find that gives us a weighted completeness of 1.5%. Weighted completeness, again, being the number of packages that you can support in a given tool. So if you implement the whole baseline, which is about 340 of those 900 something instructions, you're only able to support like 1.5%. So what happens when we start adding in the SIMD instructions in the order they appear chronologically? With MMX, you're still around the same. If you try with SSE, this is all 4 generations of SSE, you get a little bump. It goes up to about 5%. But where it gets interesting is the instant you add both of these, you immediately hit 99% of all packages. And the reason that the jump is so steep is actually because the top instructions by importance in both these extensions are actually used by the libc to optimize memcopy and memcompare operations, and that's why they're so ubiquitous. And because Ubuntu distributes as a binary distribution, we find that the newest SIMD extensions, AVX and AVX 512, aren't really used by much. About 0.2% of packages rely on them. So, so does it mean that you actually need to support all of the SSE and MMX instructions? Because that's a whole bunch. Not really. There's again, just importance within the set is skewed. So another question you may have is, what's wrong with benchmarks? Why are benchmark suites that with known and loved for a long time? Why not use them? Well, so we decided to check that as well, and I'm showing you the top 10 mnemonics. This is raw data, not weighted by package importance. And as we can see, they're roughly in the same ballpark, right? Other than these instructions that I've highlighted, which if you look at the rest of the tail in the others, they're actually just, the orders have changed. They're in the next 10 or so. They just moved around a bit. So it looks pretty good, right? So this, what happens when you take package importance into account? This graph is showing on the x-axis instructions ordered by instruction importance in the Ubuntu dataset. The line again shows you the same for the Ubuntu dataset. The dots and X's are for benchmarks. So what we find is that the benchmarks tend to be overall decently representative. These are spec and parsec again, if I seem to have forgotten to mention. Although their ordering is all over the place. Any dots under the line are less important to the benchmarks than they are to Ubuntu, and vice versa. Now, an important thing to notice is there's a whole bunch of X's down here. These X's are where the instruction has a certain importance to Ubuntu, but does not occur at all in the benchmarks. For example, some of these may actually be as high as 50%. One of the kind of surprising ones that we found was the lock prefix, which makes an instruction atomic, does not occur at all in the benchmarks, and hence that's a pretty important instruction for the Ubuntu dataset, but it doesn't occur at all. So anyway, there's a lot more data in the paper. The differences in popularity of the feature sets. Feature sets are like binary logic instructions, the various SIMD extensions, etc. There's instructions. We have data about instructions that don't occur at all, but maybe they're targets for deprecation. Another thing is they could be an artifact of the fact that we've used a binary distribution as our data source, whereas if you were compiling from source, maybe those instructions will be used. And so on. There's quite a few. There's quite a lot more data in the paper. Anyway, so I hope I've convinced you that that we don't, when you're deciding how to, when you're building a tool that uses the ISA, you don't need to prioritize developer effort on ad hoc approaches, and we can take a more principled approach. So the paper has a lot more data. It also has descriptions of a more detailed description of the methodology of how we did our analysis, and the code data, the data and code available on GitHub from that link, and the visualization tool is there. I'm actually going to use another minute to show you the tool. So let's. So this is, it displays the raw data set. This is not weighted by instruction importance. Now, if we were to look at, this is hard. So okay, let's take a look at SSE instructions. What we actually find is in the unweighted data set, it appears that some multiplication instruction seems to occur the most, and then an add and stuff. But if we were to look at this, which is the packages that occur in pretty much every installation, so these are the most important packages, we certainly find that move instructions become the most important, and this is in line with what we had looked at earlier, which was that most of these instructions are occurring from libraries, right? So we want to look at where they come from. Just I can get this to work, right? So libc and libglib seem to be the most the source of most of these XOR instructions. So yeah, I hope this tool is useful to visualize instruction importance. And with that, I'm done. Take questions.
So,
yeah.
Thank you very much. Any questions here? You can start.
About methodology, you only used Ubuntu, but in my experience, the distributions are often favored by by different target audiences. So not necessarily the Ubuntu audience is using important packages with binary instruction sets for HPC computing or some other.
I mean, that's fair criticism, right? Which is that, yes, our data is entirely biased for desktop and some kind of server workloads, maybe, and software that's only distributed by app. But if you're trying to build a non-focused, like a CPU emulator that you're just like trying to, or a binary translation tool that's just going to run random applications, I think having a data set that is as broad as the Ubuntu repositories is useful.
I guess my point is that why use Linux distro at all if the two most common distributions are either Windows or Android? I mean,
oh, you're saying, okay. So what was the first one? You said Debian or?
Ubuntu, you said. No, Windows.
Oh, you're saying Windows.
Windows.
Fair, but we couldn't get access to a easily programmable way of, but the same analysis can be applied for that too if someone has a repository of. Yes.
And so I would first ask other people for the question. So my personal opinion is that you are missing one dimension, which is time. Because you mentioned that MMX is not part of any more or less program within the Ubuntu distribution, which is more or less obvious because MMX is pretty old and most probably no compiler is using MMX anymore. So if you do a binary.
Mm-hmm.
So what would be interesting if you think about a journal or whatever, that would be nice to go back in time and check how has this moved, because MMX is there now for compatibility reasons and not to support it at the moment. And therefore, of course, it's difficult to say, oh, you can get rid of it. Yes, you can today, but most probably everyone within this room will immediately scream if the old applications do not run it.
Fair. We actually did run, but not that long ago. I think we went back up to 14, and our data was on 18 or something. Mm-hmm. So yeah, given that it's automated.
Part of the paper?
Sorry?
Is this already part of the paper?
No, that data is not in the paper.
Okay.
Our data set was collected multiple times, but we did keep it.
Okay.
But yes, as long as you can access the apt repositories for, and I think you can go back to like 604 or something like that. So that's very possible to run.